Hello, I'm Patty Simpson with Simpson Math. Let's use normal distribution and central limit theorem to solve a couple of problems. First, a population of 29-year-old males has a mean salary of $29,212 with a standard deviation of $2,120, and the distribution of the salaries is normally distributed. If a random 29-year-old male is selected from the group, what's the probability his salary is above $27,092? So this particular male that we're selecting from the group is part of this distribution of normally distributed data. So let's look at this distribution of data. First, we know that the mean of this distribution, which will be right in the middle, is 29,212. Remember that the mean is our peak of our normal distribution. It's where our mean, our median, and our mode sits. Then we know the standard deviation of this distribution is $2,120. So if I go up one standard deviation from that mean, I'm sitting at, well, we're going to add 2,120 to that. So we're at 31,322. Add another 2,120 to that, so that I'm at 33,442. So this is one standard deviation above the mean. This is two standard deviations above the mean. And if we go up one more standard deviation, then that third standard deviation, we're at 35,562. Then I'm going to go below the mean. So I'm going to subtract 2,120 from the mean each time. So that same distance, that same standard deviation, that same 2,120. Well, now we're at 27,100, or actually, when we go down 20, we need 8 more, so we're at 92. Then I'm going to go down another standard deviation from that. So down 2,000, let's go down 120 from that. Well, I'm going to need to break into my thousands there. So we're going to be at 20, bring down to 26, but then down 2 more, so we're at 24,000. And when I go down, I would be at, if I went down 100, I would be at 92. And I go down another 20, and I'm at 78. So 978. And if I go down one more standard deviation, down 2,000, I'm at 22,000. Down 100, you're at 858. So this is one standard deviation from the mean, this is 2 standard deviations from the mean, and this is 3 standard deviations from the mean. Remember, in that normal distribution, my peak is at my mean, and then it's symmetrically, it's symmetric on both sides. And so our dots should line up here, and in each one of my standard deviations, I have an inflection point, so that my normal distribution looks something, or this distribution of salaries looks something like that. And this 29-year-old male's salary is part of that distribution, and we want to know what's the probability that his is above this 27,092. So we want to know what's the probability his salary falls somewhere in there, or we're looking at the area under the curve from 27,092 above. And we know, because of the empirical rule, that if we go out one standard deviation from the mean, so between 27,092 to 31,322, 68% of our data falls within that range. We also know that above the mean, that above this halfway point, that half of our data, so from here to there is 68% of our data, and from here and above is 50% of our data. So half of our data falls in this area, falls above the mean. So if we just knew how much this was, I could add it to the 50% and find out that area under the mean, or find out the probability that his salary is in there. Well, because the normal distribution is symmetric, we can take and cut this piece in half. So half of 68 is 34. So 68% divided by 2 is 34%. That's between here and there is 34% of the area of the curve, or 34% of our data is going to be between 27,092 and 29,212. I'm going to add that to the 50%, that half on top, add it there, and I know that this area that I have colored, that 84% of our data is going to fall above 27,092. So, or the area under the curve is that much, or the probability that I choose someone randomly with that salary is 84%. So there, this was just a nice normal distribution. Let's change this problem up just a little bit. This time, we're going to take a sample of these 100 men. What is the probability that the sample mean salary is below 29,000? Notice that here, I'm not just pulling out one man from this distribution. Instead, what I'm doing is I'm pulling out 100 men, I'm collecting their salaries, and then I'm going to find a mean of those salaries. That sample mean is part of a new distribution. And we know that that distribution has a mean that is the same as the mean of our population. We know that from the central limit theorem. The central limit theorem tells me that the mean of this distribution of sample means, the mean of the distribution of sample means, is equal to the mean of our population. So in this case, the mean of this distribution, where these of sample means, is equal to 29,212. Then we know, because of the central limit theorem, that this sampling distribution of sample means, this distribution that this value belongs to, that the standard deviation of that distribution, of the sampling distribution of sample means, is equal to the standard deviation of our population divided by the square root of the sample size. So here I have the standard deviation is 2,120. We're dividing that by the square root of our sample size is 100. So the square root of 100. So we're really doing 2,120 divided by 10, which is just equal to 212. So we have this new distribution of sample means. This sample mean belongs to a new distribution of those sample means. And we know that one is also normally distributed. The central limit theorem tells me no matter what this distribution was, this distribution of sample means would be normally distributed. And so I can draw a picture of it as well. And we know that the mean of this distribution is 29,212. I'm going to do the same thing I did before, where I add on my 3 standard deviations. So I'm at 29,424, and then 29,630, and then 29,848. So notice that the standard deviation here is shrunk. In the standard deviation of our sampling distribution is smaller based upon that sample size. Depending, the bigger the sample size, the smaller your standard deviation. Then I'm going to go backwards, so that's up 3 standard deviations. I'm going to go back 3 standard deviations just to draw my distribution. And I'm sitting here at 29,000 even. If I subtract off 2012, well, now I'm at 28,000. Go down 200, I'm at 800, so 700 and a little more than 200. So I'm at 88. And then I'm going to go down another 212. So I'm still at 28,000, but now I'm at 576. So I just subtracted that 212 each time to get my standard deviations, or this 1 standard deviation below the mean, 2 standard deviations, and 3 standard deviations. Again, my mean is my peak. Mean, median, and mode are all the same in that normal distribution. It's nice and symmetrical. And then we've got our inflection points there. And as I draw my normal distribution here, this distribution is the distribution of sample means. So if I went around and collected 100 men from this population and asked them their salary and found the mean, that sample mean would be part of this distribution. Notice that there are 2 separate different distributions. This is the distribution of actual salaries from the men. This is the distribution of means that we have calculated from 100 salaries. So now we want to know what's the probability the sample mean is below $29,000. So if we look at this end, we're below that end. And there's a couple of different ways we could do it. Notice that this and that are complements of one another. You know, on this end, we've just figured out that this part, based upon that empirical rule, from here and above is 50%. So from here up is 50%. This little sliver is 34%. We just figured all that out right there. And so we know that 84% of my data falls within here. That means that if I take the whole curve, that 100%, and I subtract the 84%, I'm left with 16% in this area. So there's 16% of my data, or 16% of the curve. The area under the curve lies within this portion. So the probability that we get a salary, a mean, that sample mean salary is below 29,000 is 16%. So big difference here. Here I just collected 1 salary from 1 man. Here I collected a sample of 100 men, got a mean from that sample, and it was part of a new distribution. So when it was just normally distributed, I just used the numbers that we had to draw my distribution. But when I collected a sample, I had to figure out then my standard deviation for this new distribution. Math Made Simple at Simpson Math. Thanks for watching.